In the last few videos, we introduced a different way of representing curves, right? These parametric curves. We still had our variables x and y, and then we had this parameter t. Now what we're going to look at is look at a brand new pair of variables, right? So we're not going to be using x and y, and we're not going to be using t, but we're going to introduce the idea of representing points and curves using polar coordinates, right? So polar coordinates is it's a completely new coordinate system, but the good thing is that this coordinate system will be related to our more familiar rectangular or Cartesian coordinate system. So let's see what that relationship is, and then just kind of introduce a few ideas. Right, so I'm going to draw our, let's start with our xy plane. So x and y, and so let's say we're going to try to represent this point, right? So here's our point P. Well, in a rectangular coordinate system, we would essentially measure this distance here. In fact, let me draw this down. And then this distance here would be our x, right? That's our horizontal, I guess you could call it a displacement. And then this distance here, let me go across there. That's our y, right? So that's y. And then we use this convention. So it's going to be an ordered pair because we have a pair of numbers that we use to represent this point, put it in parentheses, and then we have x comma y, right? So that is our rectangular or Cartesian definition for our coordinate system. So that's how we can identify a particular point. All right. Well, if you think about it, I've drawn this picture. Well, there are some other things I could add to this. And those additions might give us a different way of defining the point P. So let me add a couple things here. So instead of looking at these horizontal and vertical distances, what if we look at, let's call it a radial distance, like starting at the origin, right? Everything is with respect to the origin. Instead of going either straight up or straight down, what if we went on this kind of sloped line right there? So what if we use that distance? And then once we draw this line, notice automatically I can almost see a right triangle here. And in that triangle, we have angles. So I'm going to identify just one angle, and I'm going to use theta to represent this angle, right? And our theta is always going to be measured from the positive horizontal. So I'm actually going to put a little arrow there showing that we start at the positive x-axis, and then we go counterclockwise until we hit this line here, and we can actually call that a ray, right? Or I should say line segment here. Now this line segment, depending on where P is, like if P was closer to the origin, then my blue line segment wouldn't be as long. And if it were further away from the origin all the way out here, then it would be longer. So it will have a distance that will change, and we're going to represent that distance by the letter R. And yeah, so now we can represent the same point P with a completely different pair of variables. We can say that whatever this distance is, the convention is we put that distance first. So we put our R as our first value in our pair. We're still going to use a pair, just a pair of different variables. And then we use whatever this angle is, theta, as our second value in our ordered pair. And so now this ordered pair, r comma theta, as we define it here, is how we get the polar coordinate or the polar coordinate system. All right. Now, we could spend a lot more time sort of exploring this idea of the polar coordinate system, and I will in a subsequent video kind of give you a way you can visualize polar curves, right? But I'm just going to introduce the ideas at a very basic level here, because our goal isn't really to spend a whole bunch of time talking about polar coordinates, but more so we want to think about, okay, getting polar curves, and then think about those fundamental things in calculus like slope, area, length, right? So that's kind of our goal, but I didn't want to just jump right in and just give you some formulas. I wanted to at least give a little background about the system. All right, so there is the idea. So r is the distance from the origin to whatever the point is, and theta is the angle that is made by the positive horizontal axis and then the ray or the line segment going to that point. All right. Now let me add just a few more things here. Now in terms of theta, if we think in terms of like our unit circle and where our special angles are located, we know that the positive horizontal axis corresponds to, in fact, let me do this in blue, corresponds to theta equals 0. That's one thing, right? So if we start with 0, that defines our positive horizontal axis, or this ray right here. And we know going due north, right, that would be pi over 2. And again, we love radians, so everything's going to be in radians. This ray right here, let me add an arrow. Let me add arrows there. So going due west, that is pi. So theta equals pi. And then going due south, that is theta equals 3 pi over 2. And once we've made it like one full revolution going around, then we end up getting back to, again, the same position here, positive horizontal axis. But now we would have gone 2 pi radians, right? And you can see, so right away, you can see just by making a full revolution, we could have different values of theta that would represent the same point. So, that's a little bit different than when you think about your x comma y ordered pair. If I give you a specific value of x and then a specific value of y, or let me put it this way, if I pick a particular point, it will have exactly one ordered pair that defines that point. Whereas I can have actually infinitely many ordered pairs that can represent the same point in the polar coordinate system. So just to give you an idea of how you might plot something like this, right? And again, like I said, in a subsequent video, I'll have some fancy plots just to show you. But here, the rectangular coordinate system be based on a rectangular grid. A polar coordinate system is based on let's say, a circular grid built with these circular, or I should say concentric circles. And let's start with the unit circle. I'm going to put everything dotted here. So let's say that's a circle of radius 1. Here is a circle of radius 2. And I'm just going to add a third one. Let's say here's a circle of radius 3. Right? All these circles, even though my sketches aren't great, I apologize for that. The circles, they're all centered at the origin, and in a polar coordinate system, the origin is referred to as the pole, right? So the pole is just a synonym for origin. We tend to use that. So that's what I have there indicated in green. And then we have the different radii. So our unit circle radius 1, then this one would be radius 2, and then this one would be radius 3. Now, I don't know if you've ever used polar coordinates before. You may have come into contact with polar, or I should say, polar graphing paper, right? Graph paper. So what typical polar graph paper would have, it would have those special angles. So again, I'm just going to do some stuff in the first quadrant. That's all I'm going to do. And so we know that this is theta equals 0, and then this is theta equals pi over 2. And then, like, if I were to bisect this, so right in the middle would be pi over 4, 45 degrees. But again, we like our radians, so we have this, pi over 4. And then we know 30 degrees or pi over 6 is another one. Not quite. So let me say this. Again, this is just a rough sketch. Theta equals pi over 6. And then 60 degrees or pi over 3 would be another one. It would be like right here. So theta equals pi over 3. All right. So for instance, let's say here, I'm just going to pick a couple points. So let's say I have point A. And point A has polar coordinates 1 comma pi over 2. Right? If we have that, then where would that be? So what the first thing we would have to do, either it doesn't really matter the order, but you could say, okay, well, let's locate the circle of radius 1. That's our unit circle. That's this one right here. And then locate the point that has a theta pi over 2. Well, that's on the positive y-axis, if you will. So right here, that would be point A. Right, let's pick another one. So let's say we have ordered pair 3 comma pi over 6. And again, if we know that this is a polar ordered pair, then we would have to find a circle of radius 3. That's the outer one here, the biggest one that I sketched. And then where does it intersect with the ray? Pi over 6 would be right here. So this would be point B. All right, and then let's do one last one. Let's say we have C at 0.2 comma, let's say pi over 4, right? So find the circle in the middle. This one right here has radius 2. And then we just keep going around. You notice I just keep going around, and I'm tracing out the same set of points, but I'll be using different values of theta. But if I start at 0, and then I rotate counterclockwise through pi over 4, that will take me right here, and that's our point C, right? So yeah, that's the polar coordinate system. Again, very, very basic intro. A couple more things that we're going to do before we wrap this video up. One, I want to first say, okay, well, you know, how would a polar curve, or how would we represent a curve in this coordinate system? Well, the standard way of representing a polar curve is to represent r, the radius, right, as a function of theta, right? So this is kind of the standard way to represent a polar curve. And when it's written like this, you know, it's implied that r is dependent on theta. So you'd pick your value of theta, so that would give you one of your rays. It might be a special one or a not so special one. And then based on this function, you would plug in theta, and then you would get your r, and then you'd figure out how far you are away from the origin, and then you'd plot that point, right? So that's the standard way of representing a polar curve. And this is the equation that's actually going to be a big focus for us when we get to the calculus of these curves. In a subsequent video, I will just plot some of the curves of this form so you can see just how different, even though the equation might look a certain way, you might think, yeah, I know what the curve would look like. Chances are you're thinking about the rectangular coordinates and thinking about what equations look in terms of y and x. But it actually is very interesting, very different when you switch that perspective, and now you think in terms of r and theta, right? So that's basically this. All right. So the last thing we're going to do now is to say, okay, well, what is the relationship between these four variables, right? And the reason why we might want to think about that is think of how much calculus we've done in terms of y and x. We've done a lot of calculus in terms of y and x. We have done, well, up to this point, nothing as far as calculus is concerned in terms of r and theta. So if we could find a relationship between these four variables, maybe that relationship will allow us to figure out things like slope and area and length in terms of r and theta. So how are these things related? All right, well, if you look closely, in fact, let me scroll down and just draw that little triangle again with without all the different colors. But I'm going to indicate the four variables there. And there's no particular reason why I'm orienting my right triangle like this. It is, again, we could do this in any of the four quadrants. I'm just picking the first quadrant. It's a little easier when everything is positive. So there's our theta, that's our r, that's our x, that's our y. Now, if you think back to when you were first introduced to trig, right? And it could have been in a geometry class or something like that. The definition, there's different ways you can define your standard sine and cosine ratios, but using the right triangle definition, we know that the sine of theta is equal to, in fact, let me write it down, the length of the opposite side divided by the length of the hypotenuse. In this case, based on where I have my theta, y is the length of the opposite side, and of course r, the longest of the three sides, is the length of the hypotenuse, so that will be y over r. And I can do something similar for cosine. You remember what the definition of cosine is? Sure you have. We've used it even earlier in our work with trigonometry, but it's the length of the adjacent side divided by the hypotenuse. So the adjacent side here, my little triangle, is x, and we have our r there. And then if I just look at the let's say the first equation, I can easily solve this for y. So what this tells me is that y is r sine theta, interesting, and then x is r cosine theta, also interesting. So basically all I've done with this equation right here, I've just multiplied both sides by r. And what this tells me is that if I know the polar coordinates, if I know r and I know theta, I can use these two equations to convert it back to the rectangular, right? Again, let me emphasize what this is saying. So on the left-hand side of these equations, I have the rectangular variables, right? On the right-hand side over here, I have the polar variables, and I have a really nice relationship between them, obviously involving sine and cosine. And not only this, but think about it. If I have, like, let's say I have an equation for a polar curve, r equals f of theta. What if I took the f of theta here and just kind of plugged it in there and then plugged it in there, right? Then I would have y. In fact, let's go ahead and do that. So I'm going to write another equation now. So I'm just replacing r with its function in terms of theta. So it's f of theta sine of theta. And then here I have f of theta cosine of theta. Okay, so let's kind of think about this. So now I have written y as a function of theta and x as a separate equation, also as a function of theta. But that sounds a lot like what we just did with the parametric curves. And that is exactly the case, because by plugging in f of theta here, we now have converted our polar equation to a parametric equation. Interesting. And again, this is the idea that we're going to explore further, and that will allow us to do so basically everything that we now can do with parametric curves. We first have this extra step of taking a polar curve, right? Let me go back over here. R equals f of theta. Plug it into our equations based on our right triangle. That gives us the relationship between x, y, r, and theta, and essentially eliminate the r, right? So, and then we get these parametric equations, but the only thing that's different, right? The only thing that's different is that now our parametric equations are in terms of theta. So basically, theta is just going to replace the letter T, which kind of is, to me, is somewhat poetic, right? Because the Greek letter theta represents the letter T, or vice versa, right? So that's again a very short intro into the concept of polar coordinates and polar curves. You haven't really seen any of the polar curves, but you will in the next video. And then this idea of transforming a polar equation into a parametric equation is really the key for us to do a lot of the cool calculus stuff that we need to do. All right, so you're ready to explore these further? Well, hop on over to the next video and I will meet you there.